Hi, I'm Elsa Thompson, and this is video number 2 for units 4 through 6. So, the first question is, isomers are compounds with the same molecular formula but different arrangements for each atom. For each type of isomer listed below, draw an example of the pair of molecules that fit into the definition using skeletal structures and wedge and dash notation as needed, and then explain each of your pairs using the definition of each type of isomer. Okay, so the first one is a pair of structural isomers. So these two are structural isomers because they have the same chemical, like they have the same formula right here, but they have different names. See, this one is methyl cyclobutane and this one is cyclopentane. They both have 1, 2, 3, 4, 5 carbons, except they look different, as you can see, because this one has a square in it. And yeah, anyways, so those are structural. And then a pair of conformational isomers. So these ones are conformational because they both have the same chemical formula right here and the same name, hexane. They just look a little different. They still have 1, 2, 3, 4, 5, 6 carbons and 14 hydrogens, just like it says right here. They just look different. This one has a little extra thing right here instead of going up like that. But anyways, and then the next one, C, is a pair of cis-trans isomers. So this one is cis because the two wedges right here mean that they're both facing the same direction, so they're on the same side, and cis means same. So this is a cis, and then this one is trans because there's one wedge and one dash, sorry. And one dash and one wedge, so they're different sides because they're going different directions when you look at it 3D, and trans is different, so that one is trans. This is a pair of enantiomers. Enantiomers are basically like mirror images of each other. So if you put a mirror, they're the exact same thing, just opposites. This one is the same squiggle as this one. Then you add that, and then looks the same. So it's an enantiomer. It's just the opposite. Looks exact same, just flipped. That was number 1. Question number 2. Question number 2 says, there are many ways to classify chemical reactions based on patterns and common characteristics. For example, for each of the types of chemical reactions listed below, write an example based on chemical equations showing the reactant and product structures, then explain how you classified each of your chemical equations using the definition of each reaction type. So the first one, A, this is a synthesis reaction, and this is a synthesis reaction because 2 smaller reactants combine to make one larger product. So we have H2 plus O equals H2O. So we have 1 smaller one, 2 smaller one, and then 1 bigger one for our product. And these are our reactants. Okay, and then a decomposition reaction is basically the opposite of synthesis. So we get 1 larger, this is the reactants this time, makes 2 smaller products. So we have 2 plus 2 right here. It's balanced because 2 plus 2 is 4, and then there's a 4 in front of this AL. So it just got broken apart, and then 2 times 3 is 6, and then we have 3 times 2, which is the same thing, so it's 6, so it's balanced. So we have the big one makes the small one. That's decomposition because it's like breaking stuff apart. Okay, and then we have oxidation reduction reaction. So this is what this looks like. So we have C carbon plus O oxygen, 2 of them equals CO2. So carbon dioxide. And the carbon is being oxidized because when we go to this, when we start with the products and go over, so we, start with reactants, sorry, and then go over to the products, carbon has a loss of electrons, so it is oxidized because in our, we had the oil rig thing that we would say is oxidized is lost, reduced is gain. So And oxygen right here gains, E gains electrons. I guess I was just abbreviating when I wrote this 2 days ago. And it's reduced because reduced is gain in the rig part. And then for D, we have hydrolysis reaction. Hydrolysis is, oh my gosh, hydrolysis reactions. Hydrolysis reactions happen when water, H2O, is consumed as a reactant. So we have this one, which is NH4 plus H2O. This is our water, like right here. And then it's one of the reactants, because this is a reactant. And these are our products. And we don't see H2O, we see H3O, but we don't see H2O. So it's consumed as a reactant to make this. And then hydration reaction. Reactions happen with water added. And it often acts with an acid too. So here's our acid, or like a catalyst or an enzyme or something like that. But in this one, it's an acid. And when you add H2O, it breaks the double C bond. So there's like a carbon here and a carbon here, and we have this double bond. But then it breaks right here. See, this is where it used to be. But it's not there anymore because it broke, because we added 2 H's and an O in the H2O. And then this just helps with the reaction. So that's hydration, because you add water. Hydration, to hydrate. If you drink some water, you get hydrated. So hydration. So that is number 2. Sorry if you hear my brother talking in the background. He's very loud. Yes, this is number 2. Moving on to number 3. Number 3 says, answer the following about the disaccharide maltose. I hope I'm saying disaccharide correctly. Okay. First one is, how is maltose commonly produced and what is it used for? It is commonly produced by starch undergoing hydrolysis with an enzyme, which is diastase. I think that's how you say it. Diastase. I think that's how you say it. So we talked about hydrolysis in number 2, and it is, and the common things that are used for is corn syrup and other things that require malt sugar, because maltose is malt sugar, and like maltodextrin is another thing that called malt sugar. And then B is draw the structure. So this is what the structure looks like. So this is 2 monosaccharides together. Here's the first one and here's the second one, combined by a glycosidic bond, which we'll talk about in C. So here it is in all its glory. And then without the bond, when you break it apart into glucose, like just this half of them, I'm just going to draw one half. So you'd have the O, and then go down, and the H, and then the OH. And then you'd have the H right here, but then you'd have an OH, but when they combine together in the glycosidic bond, it created just this little O right here. Speaking of which, the glycosidic bond is this part. It looks like this, and it is right here, more specifically right here, according to our textbook. And the name of this bond is A1-4, because it's A because it goes in the downward direction. This one goes in the downward direction, so it's A. That's how I remember it. And then 1-4 because when we count our carbons starting from the oxygen going clockwise, this one is 1, 2, 3, 4, and this one is the same thing, 1, 2, 3, 4. So it's 1 goes to 4. So that would be A 1-4. And I named carbons. That was just a note for myself. And then D says, draw a chemical equation for the hydrolysis of maltose to form 2 monosaccharides, showing structures of all the reactants and the products. So I drew what it would look like on this side over here without the, let me finish it. Choo-choo. I'm not going to draw the rest of the hydrogens. Sorry. I think those are implied. So this is what 1 looks like by itself. Zoom in. Whoa. That's what it looks like. Yay. Zoom out. Okay, so the chemical equation is to form the two monosaccharides is it undergoes hydrolysis, like I said, or it goes like the hydrolysis of maltose to form two monosaccharides. So this is the hydrolysis of it to form those. So this is on the these are our products right here. No, I mean our reactants. So sorry, our reactants. And then here's our water for the hydrolysis. And then right here is the part that is maltose. So maltose has equation of, it's called C12H22O11, because if you count all those out, that's what it comes out to. And then when it reacts to create the products, it forms glucose. So here it's named glucose, and it's just, the glucose is a monosaccharide. So here's our one of our glucoses, and two of our glucoses that look like that. So the glucose has C6H12O6, just like, wow, when you add, it has the same, so you have two C's, right? It makes 12. Whoa. Science. Anyways, so that was my video. Thank you so much. I hope you enjoyed. Have a good day. Bye.